Welcome to today's lecture on pattern avoidance. In this season, we will explore several key topics related to avoidance of a specific pattern in sequences and structures. The outline of the talk will include, first, a brief introduction to the idea of pattern avoidance and why it's significant. Second, we will then dive into Two's theorem, a fundamental result in this area. After that, we will discuss what pattern avoidance actually means in more detail. Following that, we will explore famous two-Morse word, which is a fascinating example of a sequence avoiding certain repetitions. Finally, we'll move on generalization, looking at rational powers, abelian powers, and other extensions that arise from these ideas. By the end of this lecture, I hope provide a strong understanding of these topics and their applications, especially in fields like combinatorics and theoretical computer science. Let's begin by looking at one of the earliest significant results in the study of pattern avoidance. Two's theorem, first presented in 1906. Axel 2 proved that there exists a word over a ternary alphabet, that is, an alphabet with three distinct symbols that does not contain any two consecutive equal factors. These are known as square-free words. Essentially, a square-free word is one that avoids repetitions of the form XX, where X is any block of characters. This result was groundbreaking at the time because it showed that it's possible to construct infinitely long sequences without repeating patterns, which has important implications in areas such as combinatorics and theoretical computer science, particularly in avoiding redundancy in coding and encryption schemes. We build on this concept as we explore other forms of pattern avoidance, but Two's work set the fundamental for much of what followed. Now that we have introduced Two's theorem, let's look at an example to make the concept clear. As the theorem states, we can construct a word over a ternary alphabet, meaning using three different symbols, such as A, B, and C. That does not contain any two consecutive equal factors. Here's an example sequence. You can see the pictures. So if you look closely, you will notice that none of these segments repeat any block twice in arrow. For instance, you won't find a repeating pattern like ABB, ABC, ABC, where the block ABC occurs twice consecutively. In general, Two's result assures us it's possible to construct infinite line sequences where no block, no matter how small or large, repeats immediately after itself. This avoidance of XX, where X is any finite block of symbols, form the basis for many future studies in this area. Now, before we go further, let's define some important terminology that we will use throughout the talk. First, the length of a word denoted by, like absolute value of W, is simply the number of the letters or symbols in the word. For example, if we have a word W, it is equal to A1, A2 till AN, where each AI is a symbol from an alphabet A, then the length of the word W is N. For instance, In the word ABC, the length is free because it consists of three letters. In formal terms, Ken would say that absolute value of ABC which is equal to 3, something like that. Additionally, for the empty word, which contains no letters, the length is defined as 0. This is denoted by, absolute value of epsilon, or we call that length of epsilon, which is equal to 0. Okay, understanding this basic terminology will help us when discussing pattern and their lengths as we move forward. Next, let's expand on the terminology by defining a few more important concepts: factors, prefixes, and suffixes. Given two words, U and V, over an alphabet, it would be non-empty words. First, we say that U is a factor or substring of V if we can write V as W1, U, W2, meaning that U appears somewhere in the middle of the V, with potentially some letters before and after. Second, U is a prefix of V, can be written as UW, meaning that U appears at the beginning of V. This relationship is denoted by like U less than V. Finally, U is a suffix of V. If V can be written as WU, meaning that U appears at the end of V. Additionally, it's important to note that a distinction that is often confused. A subword is not necessarily the same thing as a factor. The key difference lies in whether the components are continuous within the word. A subword might not appear as a contiguous block, whereas a factor must be. Let's now define an important concept in pattern awareness: the square word. The word W is called a square, if it can be written as WW, where W is some non-empty word over the alphabet. In other words, a square word consists of two consecutive repetitions of the same subword or factor. It's better I say that factor. Here's an example. The word tutu is a square because it can be split into 2 and 2, two identical parts. On the other hand, the word banana is not a square because it cannot be split into consecutive identical factors. Okay? So recognizing a square words is important for understanding how pattern can be avoided or constructed in combinatorics on word. Building on the concept of a square words, let's now look at some key properties of a square words. First, the length of a square word is always even, if it would be actually even finite word. This makes a sense because the word is formed by repeating another word twice, so the total length will be twice the length of the original. Second, by definition, a square word always has form UU, where U is any non-empty word. This means that no matter what the original word U is, once it's repeated twice, the result is a square word. Okay? Now let's talk about pattern avoidance. This concept is central to understanding how we can construct sequences that do not contain certain repeated patterns. We say that a word W avoids a pattern P if there is no factor of W that can be obtained by replacing the variable in P with non-empty factors of W. So in other words, the pattern W consists of some placeholders or variables, and if we can replace those variables with parts of the word W, and it can create a factor of W, then the pattern is not avoided. If we cannot find such a match, then the word avoids the pattern. For example, if P is a pattern like XX, and we can find two identical consecutive factors in W, then W does not avoid the pattern. The goal is to construct words that do not contain such matching patterns. To clarify the concept of a pattern avoidance, let's look at a specific example with the pattern XYX, where X and Y represent non-empty factors of a word. First, consider the word ABC, ABC. This word does not avoid the pattern XYX. Why? We can identify X as AB and Y as C. Substituting into the pattern XYX, we get AB, C, AB, which is indeed a factor of ABC, ABC. So the pattern XYX is present here, meaning this word doesn't avoid the pattern. Second, consider the word A, B, C, D, E, F. This word does avoid the pattern XYX because there is no way to match the structure of XYX with any repeated non-empty factors. Each part of the A, B, C, D, E, F is distinct, and no factor of the word can be rearranged to fit pattern XYX. Okay, this example helps illustrate how pattern avoidance works in the practice and why it's significant in understanding repetition in sequences. Now let's then turn our attention to the challenge of avoiding a square in infinite words, particularly over a binary alphabet where the number of symbols in the alphabet A is 2. Why? It is possible to avoid squares in finite words. Something quite striking happens when we consider infinite words or a binary alphabet. The answer to whether such a word can avoid squares is a firm no. In fact, there is a well-known result that proves there is no infinite binary word that avoids squares entirely. In other words, no matter how we can construct an infinite sequence of zeros and ones, eventually we will always find a repeated block of symbols, such as 0, 1, 0 or 1, 0, 1, 0, which forms a square. This result highlights the inherent difficulty of avoiding repetitive structures, especially in more constrained alphabets like the binary one. Now let's shift to the case of avoiding squares in word formed from a ternary alphabet, that is, an alphabet with three symbols. Unlike the binary case, where avoiding squares is an infinite word was impossible, with a ternary alphabet, The answer is yes. It is indeed possible to construct both finite and infinite words that avoid squares. For example, consider the finite word APACABA. This word avoids squares because no part of it consists of two consecutive identical blocks. Similarly, we can extend this to infinite words. Here's an example. A, B, C, A, B, A, B, C, blah, 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 blah. This infinite word successfully avoids squares throughout, meaning there is no part of this sequence where a square appears. This result is quite interesting because it shows that as the size of the alphabet increases, it becomes easier to avoid squares, even in infinite constructions. Now let's talk about morphisms, which are important tools in the study of sequences and pattern avoidance. A morphism is a mapping between two alphabets like A1 and A2 that is satisfy certain conditions. But here formally, it's a map like phi from A1 star to A2 star, where the asterisk indicates that we are working with words of arbitrary length over those alphabets. So the key property of a morphism is that it must preserve concatenation. In other words, if you have two words like X and Y in A1, then applying the morphism to the concatenation of X and Y is the same as applying the morphism to X and Y separately, and then concatenating the results. This is expressed like as phi of xy, which is equal to phi of x times phi of y. Times we can say that concatenation phi of x and phi of y for all x and y in A1 star. A morphism is uniquely defined by how it maps each element of the alphabet A1 to a word in A2. Once we know the image of each letter, we can extend it in the entire words. For example, if we have a word like W consists of letters A1, A2 till AN, the morphism applies the word as phi of W, which is equal to phi of A1 concat phi of A2 till phi of AN. Actually, morphisms are crucial in constructing words that avoid certain pattern and in analyzing the structure of infinite sequences. Next, let's discuss the two most morphisms, which is a well-known example of how morphisms can generate interesting sequences. The two most morphisms, mu is defined over the binary alphabet 0 and 1 and maps its symbol as follows. Mu of 0 goes to 0, 1, and mu of 1 goes to 1 and 0. So if you apply the morphism to a word, each 0 in the word is replaced with 0 and 1. And which one is replaced with 1, 0. For example, if we start with the word 1101, applying the morphism gives mu of 1101, which is equal to mu of 1, mu of 1, mu of 0, mu of 1 is 10, 10, 0, 1, 10. So the two more sequence generated by iterating this morphism is important because it avoids certain patterns like squares and has fascinating properties that make it appear in various areas of mathematics and computer science. Here we discuss the idea of fixed point of morphism. When we apply a morphism, like phi, repeatedly to a letter A, we generate a sequence of words like A, phi of A, phi 2 of A, phi 3 of A, and so on. If the length of these words grows infinitely, meaning, absolute value of phi of k of A goes to infinity, there can be a limit of this sequence. This limit, denoted by U, is a fixed point of the morphism, meaning it satisfies like here. U, which is equal to phi of U. In other words, applying the morphism to U doesn't change it. It is stable under the action of phi. Another way to express this, it means y, which is equal to phi of omega of A. This notation indicates that the word U is obtained by infinitely applying the morphism phi starting from the letter A. Fixed points of morphisms are particularly important in generating infinite sequences, such as the two-more sequence, and they play a crucial role in pattern avoidance and word structure. Finally, let's explore the two-more word in more depth, which is an infinite binary sequence generated by iterating the two-more morphisms we discussed earlier. To recall, the two-more morphism is defined as 0, mu of 0 is 0, 1, and mu of 1 is 1, 0. Starting from 0, we can iterating applying the morphism. Okay, like 0 goes to 0, 1, 0, 1. Instead of 0, you put 0, 1, and instead of 1, you put 1 and 0, and so on. So, as we apply the morphism, we generate longer and longer sequences. The infinite limit of this process is called the two-most word and is denoted by T. Formally, this word is the fixed point of the morphism, given by actually T, which is equal to phi of infinity of 0. You can see that. This sequence avoids squares, meaning it contains no two consecutive identical factors of symbols. The two-most word has many fascinating properties and applications, appearing in areas such as combinatorics, number theory, and even computer science. The two-more sequence was independently discovered by several mathematicians, including Axel II in 1912, Marson Morse in 1921, and others, showing its depth, historical roots, and importance. Let's now look at over free words, another important concept in combinatorics and words. An overlap is a word of the form A, capital X, A, capital X, A, where A is a letter and X is a word, which could be empty also. In this structure, the letter A occurs 3 times, with some repetition of a block in between. For example, the word E-N-T-E-N-T-E is an overlap because it has the structure like E, N-T, E, N-T, E, where E is the repeating letter and NT is the repeating block. A major reason proved by Axel II in 1912 is that 2 Morse 4 is overlap free. This means that in the infinite 2 Morse sequence will not find any subsequences that has the structure like A, X, A, X, A. This property, along with the fact that 2 Morse 4 avoids squares, makes it a fascinating example of a highly structured but non-repetitive sequence. Let's now look at an example of a square-free word generated by a morphism. Consider the morphism phi defined over the alphabet A, B, C with the following rules. Phi of A is ABC, phi of B maps to AC, phi of C maps to B. Starting from the letter A, if we apply the morphism repeatedly, we generate a sequence of words. The fixed point of this morphism, that is, the infinite word that remains unchanged when the morphism is applied is, I have this word you can see in the picture. U, which is equal to A, B, C, A, C, B, B, blah, 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 blah. This word is a square free, meaning it contains no consecutive repeated block or factor of symbols. This property makes it an important example in the study of non-repetitive structures. So this construction shows how we can use morphisms to symmetrically generated words that avoid certain patterns, such as squares, which is a crucial in area like combinatorics. To conclude, let's briefly explore some generalization and further directions in the study of pattern avoidance. Actually, pattern avoidance, we have already discussed avoiding specific patterns like squares and overlaps. This idea can be extended to more complex patterns across different alphabets and word structures. So in the second, we can avoiding uh, fractional powers, A related concept is avoiding fractional powers, which are repetition of parts of a word in non-integer modes. For instance, avoiding 3 over 2 powers means constructing word where no subsequence appear 1 over 5 times consecutively. The famous Tejan conjecture about fractional powers was recently proven, opening up new avenues of research in this area. Counting word actually counting words, another interesting question is determining the number of the words of a given length n that avoid a specific pattern. This combinatorial problem is challenging and has connection to generating functions and other mathematical tools. And therefore, abelian and additive powers. Finally, there is the notion of avoiding abelian powers and additive powers, where we can consider patterns in the term of the permutations or other more general operations. For example, an abelian square is a word where the letter in 2 consecutive blocks are rearrangement of each other and rather than exact matches. So we will see in the next slides. So this generalization show how rich and deep field of pattern avoidance is and how connected the various other areas in mathematics and computer science. Let's revisit the idea of pattern avoidance with a more formal definition and an example. A pattern is a finite word over an alphabet of variables. For instance, The pattern for a square is simply XX, where X represents any word. This is why we say a word avoids squares if it doesn't contain two consecutive identical factors. In general, an occurrence of a pattern P in a word is a morphism HP, where the variables in the pattern are mapped to actual word in the alphabet. For example, if we have the pattern XYYX and a word like ABA, BB, BB, ABA, this sequence represents an occurrence of the pattern because we can map X equal to ABA and Y equal to BB. Thus, ABA, BB, BB, ABA is an occurrence of the pattern XYYX. The ability to recognize and avoid patterns like this is essential to a study of combinatorics on board, actually, and it would be challenging somehow. Now let's move on the concept of unavoidable patterns. An unavoidable pattern is a pattern that will be inevitably appear in any sufficiently long word over a given alphabet. The pattern X, representing a single letter, is clearly unavoidable because any word contains individual letters. Similarly, the pattern XYYX is also unavoidable, regardless of the word. If it is long enough, you can always find this pattern of repeating letters or blocks. There is also a general construction rule. If P is an unavoidable pattern and X is a new variable that doesn't appear in P, then the pattern PXP is also unavoidable. This means you can embed new pattern between copies of P and they will be still unavoidable. Unavoidable patterns are important actually because they define constructions on how we can avoid certain structure when constructing words. Now let's introduce Zemin patterns, which are a special family of patterns that are all unavoidable. We define the Zeeman patterns Zn inductively as follows. Z0 is x1, Zn is Zn minus 1, xn, Zn minus 1. This means that the first Zeeman pattern Z0 is just a single variable x1. As we move to higher Zeeman pattern, each pattern is built by embedding the previous pattern on both sides of a new variable. For example, Z1, which is equal to x1, x2, x1, Z2, which is x1, x2, x1, x3, x1, x2, x1. Okay, I will add you in the problem solving, do something like that. What's important about Zeeman pattern is that they are unavoidable. The theorem states that all patterns in this family Zn will inevitably occur in any sufficiently long word over any non-trivial alphabet. So these patterns play a key role in understanding the unavoidable structures that must appear in the sequences, and they provide a symmetric way to generate such patterns. Wrap up our discussion on unavoidable patterns. We have an important theorem from Zeeman and others established in the late 1970s and early 1980s The theorem states that a pattern is avoidable if and only if it is irreducible. So this means that a pattern can only be avoided in an infinite world if it cannot be reduced to a simpler and unavoidable form. If a pattern is irreducible, it is inventable that will appear in sufficiently line words. Zemin work laid the foundation for understanding the structure of unavoidable patterns, and subsequent researchers like Bean and McNulty expanded on these ideas. Their combined um, work has had significant implications for combinatorics on word and pattern avoidance. So now let's talk about abelian powers, which generalize the concept of squares and repetition by considering permutations of letters within factors. First, we define the parity vector of a word U, denoted by psi of U, as the vector the occurrence of each letter in U. For example, the parity vector of the word ABBC counts how many times each letter from the alphabet appears. I mean, psi of ABBC, which is equal to 1, because A appears one time, 2, because we have 2B, 0, and 1. So, I mean, where 1 occurs to A and 2B, B, and so on. Now, two words X and X prime are said to be abelian equivalent if their parity vectors are the same. In other words, X and X prime have the same number of occurrences of each letter, but possibly in different order. An abelian square is formed when two consecutive factors are abelian equivalent. For example, the word ABEC followed by CBAB form an abelian square because both factors contain the same number of each letter, 2B, 1A, and 1C. This concept is useful when we study more flexible forms of repetition, where exact order doesn't matter as much as the frequency of symbols. Currently, let's address a famous open problem that was the first posed by Paul Erdős in 1961. Are abelian squares avoidable over a finite alphabet? In the other word, is it possible to construct an infinite word over a finite alphabet that completely avoids abelian squares, where consecutive factors are abelian equivalent? So the answer came 1962, when F. Dukimov showed that yes, abelian squares are avoidable, but only if we use an alphabet with at least 25 letters. However, the story doesn't end there. Pleasant later proved in 1965 that 3 letters are not enough to avoid abelian squares, but 5 letters suffice. This naturally leads to the next question. What about an alphabet of 4 letters? See? One of the most significant results in the study of abelian squares in the construction of Kra-Anen word. This word is a fixed point of a uniform symmetric morphism, defined by a specific morphism phi, as you can see in the formula on the slide. The key property of this word W is that it avoids abelian squares entirely. This was a breakthrough in the study of abelian square avoidance, as it provided an explicit construction over a finite alphabet of size 4, answering Erdős question about the minimal alphabet size for avoiding abelian squares. The symmetry and uniformity of the morphisms make the carry-on word not only an important theoretical result, but also a beautiful example of structure and avoidance in combinatorics and words. Next, we dive into the concept of additive powers. Here we consider an alphabet that's subset of the integers 1, 0, 1 till n. The natural question we ask is, can we avoid having k consecutive words that have the same sum? For example, consider the sequence 0, 1, 0, 3, which sums to 4. The answer, interestingly, is no. And this result is actually a corollary of the famous Zimmermann theorem. This theorem, originally formulated in the concept of arithmetic progressions or additive combinatory, applies to our setting, showing that it is impossible to avoid consecutive sum over a long enough sequences. In the following up to the previous question, we now ask, can we avoid having k consecutive words with both the same sum and the same length? For k equal to 4, the answer is yes. In fact, there exists a binary word that avoids abelian 4 powers. This result was proven by Deking in 1979. However, this naturally leads us to ask, what about smaller values of k, like k is 3 or k is 2? These cases remain more complex, and they pose enduring questions for the further explanation. The transition from 4 powers to smaller powers is a delicate issue, as a smaller power are typically more challenging to avoid. In this slide, we examine the result from 2011 by Cassie, Corrier, Scheffler, and Shalit, where they proved a fascinating theorem about additive cubes. They demonstrated that the fixed point of a particular morphism avoids additive cubes over alphabet 0, 1, 3, 4. The morphism itself is defined as follows. 0 maps to 0, 1, 0, 3, 1 maps to 4, 3, 3 maps to 1, 4 maps to 0. The fixed point generated by morphism avoids additive cubes, meaning that no consecutive triples of words within this sequence have the same sum. This sequence starts as you can see in the screen, 0, 3, 1, 4, blah, 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 blah. And it contains indefinitely while meaning maintaining the property of avoiding additive cubes. This result extended our understanding of morphisms and additive patterns, providing a beautiful example of how a morphism can be used to construct complex yet structured sequences. And to conclude, we arrive at an open problem in this domain. Are additive squares avoidable over a finite alphabet of integers? We have seen numerous results about avoiding additive cubes and higher powers. But the question of where additive squares, that is, two consecutive or the same sum, can be avoided on a finite remains unanswered. This is an intriguing question that still invites further explanation and research. It is questions like this that push the boundaries of combinatorics on board and encourage deeper investigation into pattern avoidance, both in classical and additive form. Okay, I think it's enough for a second lecture. See you.